Hello, welcome back. So today we're going to go through an example of the assembly process. Last time we went through the introduction of that, we went over some initial examples and sort of looked at how you put the local elemental connectivity stiffnesses and forces and tractions into the global setting. Here we're going to go a little bit deeper with a little bit more complex example. And then after we do this by hand, we're going to go ahead and try to generalize it a little bit to put it in MATLAB, which will basically allow us to do the hand calculations easier. And then we can then run Abacus with the same example and see that that gives the same result and determine if it gives the same result of what we're going to do here. So let's get started. We have this problem here. You can see that we have three nodes, 1, 2, and 3. Notice that this is two elements, okay, E1 and E2, and notice that I sort of mixed up the connectivity here. So instead of going 1, 2, and 3, I specified it as 1, 3, 2. So that provides a little bit more challenge to us as we fill in these global matrices. We have 2-point forces, P3 and P2, applied at those nodes. We have a fixed boundary condition here at node 1, and then we're going to make it easy for ourselves and say that E, A, L are constant, and F, the internal body force, is 0. All right, so let's get started. What we can do right away is write our elemental stiffness matrices for both of these, right? So we can have K E1, that's going to be equal to EA over L, and we'll have a 1, -1, -1, 1. Okay. And then we're also going to have KE2. It's going to look similar, EA over L. And we're going to have a 1, -1, -1, 1. Okay. So this is for the two-node truss elemental stiffnesses. You should know this pretty good by now. Now, if you remember last time, we have local connectivity defined for each one of these, or local node numbering also. So if we wanted to add the local node numbering, we could put a little L maybe here and do 1 and 2, right? And then this is also going to be 1, maybe I do it the other side, it might be easier here, 1 and 2. All right, so that's our local node numbering, how we would denote that. We can write the global numbering on that as also. So what if we use red there and wrote a G, and what is that globally? So element 1 is right here, right? And if we were to put local numbering, if we extract element 1, for example, so let's just draw it here. Maybe I'll use a different color here. So let's draw it here, element 1. So we're going to have 1 and 3. That's globally. What is it locally? Well, that would be 1 and 2 local, right? So if you remember, it always goes counterclockwise, so 3. And in this case, it's left to right. So globally, we would write 1 and 3, 1 and 3. Okay, and we do the same thing here, 1 and 3. These are going to be used when we fill in our global stiffness matrix. Let's do that really quick for the element 2. So there, we're going to have 3 and 2. So we'll have our local numbering, which will be 1 and 2, 1 and 2. Global is going to be 3 and 2, 3 and 2. Again, these are used to fill in our global matrices. Now let's write our kg, our global stiffness. So what is the size of kg? Remember, it's degree of freedom by degree of freedom, or nodes by nodes in 1D. So kg is a 3 by 3 because there are 3 degrees of freedom. So we can write that down here. And I really should be doing 2 lines underneath these because these are tensors. That's how I denote tensors on paper. So kg, let's make some space for it. So we'll have a 3 by 3. I can make it a little easier here, and let's just do some lines to split it up. So to fill these in, let's make our global numbering here. So this is going to be, our columns are here are 1, 2, and 3, 1, 2, and 3. Columns and rows, those are our global node numbering, right? So let's take element 1 first. Let's use green for that. So where does green going to go? It's going to go in the 1 and 3 positions, right? So green is going to be in 1. So this would be the 1. Here I'm pointing, let me point here. So 1, 1, remember these, we're looking at these numbers here, the global node numbers, that's where we want these from. So 1 and 1 is the first position, and then we're going to have row 1, column 3 here. So the 1 and 3 is going to be this position. So over here. And then we're going to have 1 and 3. So I'm looking, or sorry, 3 and 1, row, column, 3 and 1. That's going to be down here. And then our 3, 3 is going to be here. Okay, so that'd be element 1. So we can fill that in. That's going to be EA over L. Okay, so, and both of these, remember, we have EA over L is constant throughout. So we could actually bring that out and make our life easier. Those are all scalar values, so I can put it anywhere. I'm trying to think, I should put it maybe outside the matrix, or we can just include it here, just to be clear maybe. EA over L, and that's going to be a 1, right? And then our row 1, column 3 is going to have a negative 1. So we're going to have EA over L times negative 1. Then our row 3, column 1 is going to be a negative 1. So we'll have EA over L times negative 1. And then we have row 3, column 3 is going to be a positive 1. So EA over L times 1. Okay? Now, let's move on to element 2. Let's do that in orange. So this is going to be element, I think I make these lowercase, so E2 and E1. So here, this is going to involve, if we look over here, we're going to row, our row is going to be 3, so 3, 3. Then we have 3, 2, 2, 3, and 2, 2. So you always have to follow these global node numberings, okay, even though it seems backwards. So row 3 down here, row 3, column 3. So our first position actually goes here for element 2. So we'll use our orange, and so that's going to be a 1. So we're going to have a plus EA over L and a 1 there. So our next term is going to be row 3, column 2, and it's going to be a negative 1. So we'll have EA over L times negative 1. Move on to the second row. So row 2 globally, okay? Row 2 globally, column 3, that's going to be a negative 1. So we'll have EA over L times negative 1. And then finally, row 2, column 2, which is going to be a positive 1. So we'll have EA over L times 1. Okay, so in this case, we see that we actually have, well, these other values are going to just be 0, right? So we do need to add up along the 3, 3 position is where we actually had to sum. So those just overlap. So if we write that value then, so we're going to have, we can pull the EA over L out, and then we can write 1, 0, negative 1, 0, 1, negative 1, negative 1, negative 1, 2. Okay, and so that is our global stiffness matrix. Now, we want to move on then to the forces and the tractions, right? So our force and our traction are going to be Fe, in the general form was AL times F over 2, 1, 1, right? And then our traction for the element is TL over 2, 1, 1. So we just need to use the equation. If you remember, we had, that equation was F of G globally, that's a vector, these are vectors, okay, is equal to, well, we actually said it was the sort of the sum of Fe plus Te plus the point forces, right? So this should probably be a lowercase. So if we wrote those in, we're going to have AL over F times 2, right? And then we have to do the sort of same thing. So we are going to have global matrices. We have 3 nodes, so it's going to be 1, 2, and 3. Look, the numbering is similar as the global 1, 2, and 3 here. So even though our nodes are not in order, we're still going 1, 2, and 3 in our global numbering sense. So in that case, we're going to have 2 elements. I should probably leave a little more room here. And we'll put another magenta line down here. So we'll have, this would be E1 and E2. So what are our forces here? So E1, what is that going to represent? E1 is 1 and 3 globally, right? So 1 and 3. So we'll have a 1 and a 1 here. Element 2 is 3 and 2. So we'll have a 1 and a 1 here. Now that's going to look very similar for the tractions. Okay, so we would have a plus, and we're going to have TL over 2, and we're going to have the same sort of structure, E1 and E2, and those values, actually I should have written this in orange. We're using orange for our element 2. And of course, this is 1, 2, and 3 globally. Okay, so that's our TE and FE. And then we have our point forces, which is going to be 1, 2, and 3. And we said we have one at 3, it's P3. And at node 2, it's P2. And this is we have nothing at node 1. So in our case, you also remember that these things were equal to 0, we said initially. So it makes our life really easy adding these up, but you would basically just add across, and what you're left with is 0, P2, and P3 as the global force vector. A couple other notes. If you remember, the total potential energy is pi is equal to 1/2 capital Q, those are our global displacements, capital K sub G, that's our global stiffness, Q, minus Q transpose, and then our global force vector. Okay, we can do a couple of checks here. For example, is Kg symmetric? As we discussed. So if we go back and look at that, we have looking here, you can see that yes, it is symmetric. So that would get a check mark next to that. The other thing we can say about the K matrix, so we can determine the nodal half bandwidth, which remember, is the maximum of 3 minus 1, the difference between each one of those nodes numberings. 3 minus 1, we'll have a 3 minus 2, and then we add a plus 1. So that's going to give us 3. And so k banded is n times n bw, which means it's a 3 by 3. So in this case, because of that no numbering, we aren't able to save ourselves any space because we have the shifted nodes 1, 3, 2. They're not sequentially ordered. All right, moving on closer to the solution procedure, we now need to apply the boundary conditions. And so boundary conditions. Okay, and what are we going to use? We're going to use the elimination approach. And we'll write our kg. That's E A over L, 1, 0, negative 1, 0, 1, negative 1, negative 1, negative 1, 2. We have our global node numbering of 1, 2, 3, 1, 2, 3. And the question is, how do we handle the boundary condition? What boundary conditions do we have? Well, here the boundary conditions are typically the displacement type where we're doing this approach. And so in our case, we have node 1 is constrained in the x. And so what we do in the elimination approach is very simple. We just cross out any values that exist. So before I do that, let me write also, we have f of g, and that's equal to 0, p2, p3. And then we have our global displacements, which is q1, q2, and q3. So in our elimination approach, what we're going to do is cross those values out. So we use the red, and we basically just go right across with whatever we were given. So it's 1 degree of freedom. That's the degree of freedom number 1, I should say. So we cross those out, and we do that actually in all the cases. Okay, so that's eliminated, and that leaves us with the reduced stiffness matrix. Basically, it's this stuff in here. Okay, so we can write that now. K G reduced. Okay, and that's going to be equal to 1, negative 1, negative 1, 2. Okay. So what we can solve now is in our solution procedure, solve, we're going to do KGR, that's minor KGR reduced, times Q. And actually these are reduced too. So, you can put an R there, and you can put a FR there if you want. And if we wrote all that out, we'd have EA over L, 1, negative 1. Actually, I forgot to write that here. EA over L. Okay. Negative 1, negative 1, negative 1, 2. We have Q2 and Q3 equals P2 and P3. So what we do is we invert and we solve for Q. Q is equal to KRG inverse times FR. Okay, if you remember how we solve that, let's go over here. We know that if you have, let's say, a matrix, I just call it K is equal to A, B, C, and D, we need to invert that, right? So K inverse is going to be equal to 1 over A times D minus B times C, and then we'll have D minus B minus C A. Okay, that's a given equation that we have for linear algebra. So in our case, our KRG G inverse is going to be equal to L over E A 1 over 2 minus -1 times -1, and we'll have 2, 1, 1, 1. Okay, so we can put that into our equation. QR, the reduced, is going to be K inverse GR times FR inverse is equal to L over EA 2 times 1, 1, 1 times P2 times P3. Okay, we have a 2 by 2. We have a 2 by 2 and a 2 by 1 is going to give us a 2 by 1. So if we multiply that out, it's going to be equal to 2 times P2 plus 1 times P3. Okay, 1 times P2 plus 1 times P3, all times L over EA, which simplifies to L over EA 2 times P2 plus P3, P2 plus P3. Oops. P3. All right, now remember that this was actually in QR, this is actually globally, these are nodes. These are nodes 2 and 3, if you remember, okay, global. And so if we also assume for our purposes, because you remember Q1 is 0, so we basically have the whole displacement matrix now if we wanted it. Now for simplicity, let's say if P2 equals P3 is equal to L is equal to E is equal to A is equal to 1, I made everything really simplified there, then Q is equal to, QR I should say, is equal to 3, 2. Okay, so that gives us our displacement. We basically solved for the displacements that we didn't know. All right, so now we have displacements, we can get to strain and stress. So let's write those out quickly. We have Q is equal to, now this is the entire global displacement vector, 0, 3, and 2. That 0 is known from the boundary conditions. We have epsilon is going to be equal to BQ, right? And so epsilon for E1 is going to be equal to 1 over L1, -1 times 1, times Q1 times Q3. Okay, so this is B, and this is little q. Okay, how do we get that? Well, again, locally, these are the 1 and 2 positions, right? But globally, they correspond to 1 and 3. And we know those values, so we can fill it in. So we'll have -1, 1, 0, and 2. It's going to be equal to 0 plus 2 is equal to 2. So it's nice because now we can get the stress. So stress in E1 is equal to E times epsilon E1, right? So that's going to be equal to epsilon BQ, or sorry, Young's modulus times BQ, which is equal to 1 times 2 is equal to 2. That's the stress in element 1. Similarly, for element 2, we can do -1, same process, -1. Here we're going to have Q3 and Q2. That's going to be equal to -1, 1, 2, and 3, which is going to be equal to -2 plus 3 is equal to 1. stress in E1 is going to be equal to 1 then. Okay. Now we can also do, if you remember, at the last part of the lecture we talked about reaction forces. So we use the equation that was eliminated, basically the one equation that we eliminated corresponding to the one position, node 1 position. We can use that to compute the reaction force at node 1. So R at node 1 is going to be equal to K11 Q1 plus K12 times Q2 plus K13 Q3 minus F1. So if we write this, we're going to get 1 times 0 plus K12 is going to be 0. 0 times 3, and K13 negative 1 times 2, and then that's going to be minus 0, and that's going to give us negative 2. All right, so we just derived, congratulations, we just derived the entire finite element problem for this simple truss problem. It's the basis and the same structure as we're going to apply to all the other finite element problems. So it's a really big step we've done here. You know, one question we might have is, okay, how do we check this? And let's do a little extension of this algorithm we basically just went through. We're saying this reproducible. We could extend the number of elements, for example. We can mess with the numbering of the elements, and we should get similar results. So in order to move in that direction, let's now go create a MATLAB script that can do this problem, and then also check the result in Abacus. So now let's check in Abacus and MATLAB. And we'll do that in the next video.